Let's just give some examples to some of these vocab words, and maybe it'll be a little bit more understandable for you. So arithmetic sequence, our first vocab word there, give myself a little space here, is just a sequence of numbers that have a pattern. So we could say 3, 6, 9, 12. And if you look at those numbers, they have a pattern. They're increasing by 3 each time. So we could also have an arithmetic sequence that says 22, 17, 12, and so forth. And in that sequence, we're actually subtracting 5. So there's something common going from one term of the sequence to the next term. So in this first sequence, we go plus 3, plus 3, plus 3. In the second sequence, we subtract 5, subtract 5. And so these two things are examples of arithmetic sequence, but the beauty of it is the difference in each of those terms is your common difference. So in the arithmetic sequence, the non-zero difference between any term and the previous term. So in this case, the common difference is 3, 3, 3, so it's common among all the terms. In this case, the common difference is negative 5, negative 5. So this is an example of a continuous graph. So the graph is created by just drawing your pencil all the way along the actual graph. So you never have to pick your pencil up off the paper when you're graphing this particular equation. So this is a continuous graph, and it happens to be the graph of y equals x squared. The next word is dependent variable, coordinate plane actually. And coordinate plane is just our x and y plane. So we have that also pictured in the same graph or the same diagram. So our coordinate plane is just here. Our x-axis runs horizontally, our y-axis runs vertically, and it creates 4 different quadrants, and that is also a definition. So a quadrant is just any one of the 4 sections created by the 2 axes, the x-axis and the y-axis. And quadrant just means 4, because quad is 4, and so we have 4 different axes. And they're numbered such that they're numbered with Roman numerals. That's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So the next word that we're going to look at is dependent variable. And in this equation in particular, what we see and what we often see is that y is by itself and it equals something that has been given by the rule that follows the equal sign. In this case, it's a very short rule, x squared. And when we put it in function notation, remember we put f of x equals x squared. And so this value is dependent on what we put in as our x value. So because our function output depends on our input, we call the y our dependent variable. It is the output of the function because it depends on what you put into the function. So here's an example of a discrete graph. You'll notice that each of the points here and here and here, in order for me to graph this, I actually have to pick up my pencil and go to the next point. Whoops. And so when I do that, that calls this a discrete graph because they're very distinct points that are not connected in any way. The next item on our list is domain. And remember, domain is just the x values. So I'm just going to use this discrete graph to identify the x values. So the domain on here, if we look at our first point, our x value for that is -6. So we'd have a -6, and then our next value is -2. So -2. Then we have -1. We have a 2. We have 6 and 8. Now all of these are the possible values of x in this particular graph. And this brings us to our next vocab word, which is element, because each one of these is an element of the set of domain values. So that's all we're talking about when we talk about an element. It's any member in a set. So what we see here is that we can input a -6 and we get as an output +3, because the -6 +3 is this point. If we put in a -2, we would get out a 4. Now we can't put in a -4 or a -3 because those are not part of our domain. Those are not our inputs. They're not part of our domain. Therefore, we can't put it into this particular set of points, because this relationship has been determined to be just these points and only these points. Okay, so continuing on with our definitions, we have function, function notation, and function rule. So the easiest way to do that is to just start with the function notation. So we have f of x, and I'm just going to create some function. We'll say 2x plus 1. So we have to remember from our discussion in class that f is just the function name. So it doesn't matter what that letter is, it's only the name to distinguish it from any other function. We also have right there, as we talked about before, it is the input. It's also the independent variable. It's the one that you just pick arbitrarily and put it into the function. It's also your domain. So as long as you're picking a number inside your domain, then you can put it into this function. Okay, so you have your function name, your input. All of this together is called the output. Okay, and so then over here you have your function rule, because the function rule is what's going to happen to your input. So in this case, the function rule says I'm going to take the input, multiply it by 2, and then add it to 1. And that's all these things are. So a function is a particular type of relationship or relation such that there's only one there's only one output for every input. So as the definition states, a relation is a function is a relation where every element of the domain or the input is paired with exactly one range value. And all of this is the function notation. So we just covered the function, function notation, and function rule. Okay, so this is an example of a mapping. So it just illustrates how all the elements of the domain, and the domain is always on the left-hand side, match up with the elements of the range. So you'll notice we have an element in the domain of -2, and it matches up with 11. So we actually can use the pairing up of the domain with the range to create our next vocab word, which is an ordered pair. So -2 and 11 actually would be plotted on the coordinate plane at -2 and 11. Our next element in the domain is 4, and it's paired up with 3, and so we could plot that point. Our next element is 7, and it's mapped to or paired up with the 9 in the range, so that's also another ordered pair. and the final element in the domain is 10, and it's paired with 0, the element in the range, to make the last ordered pair. So this is another example of a discrete graph. We created it using our domain and range map. The mapping just links one element from the domain to the corresponding element in the range, and we can easily graph it on a coordinate plane. All right, so we just did mapping and ordered pair, and so now we can move on to origin, which we can see right here on this graph. And so the origin is just the point where the x-axis meets the y-axis. So it's this point right there. That is the origin. Okay, so moving on, we already did quadrants, and so now we need to look at the range. So we talked about the range, and the range is just all the values that y can be in that relation or function. So it's the values along the y-axis or the second coordinate in each ordered pair. Okay, our last three terms are really straightforward in the fact that we've already been talking about relations. A relation is just a set of ordered pairs. So everything that we've been discussing have been a bunch of ordered pairs, and then we just group them all together. This graph that you see here is a set of ordered pair because I could actually put points all along this particular graph that would help to define that graph. So all of these, sorry, that didn't quite go on. All of these points are part of the collection of ordered pair that create this relation. Okay, so recognize that anything that is a continuous graph like this is a relation. Even discontinuous graphs are relations because something has caused them to all be put together for some reason. We don't always know what that is. In this case, it happens to be a quadratic equation, but it all is dependent on the situation that created those points to be part of the same unit. All right, so now the vertical line test, what you have to think about in the vertical line test is that a vertical line is just an x value. So these lines might not be terribly straight, but I'm going to try to draw them. All right, so there's a vertical line. Here's a vertical line and a vertical line. And you notice that we're just creating lines that are associated with x values. So all of these vertical lines are simply just saying that that's an x value, and each of those x values cross the graph that we have exactly one time. So it crosses, that vertical line crosses there, that one crosses there, that one there, and so forth. So each of these vertical lines simply cross the graph one time, which then leads to the fact that it is a function, because that's telling us that for every value of x, there's only one value of y. And so that takes care of our definition of the vertical line test, because we can see clearly that when we do that and we cross our graph only one time, then we must have a function. Okay, so we cleared all of that mess off the graph so that we can look at our last definition. Our last definition is zeros. And for right now, we're just going to look at them graphically. So graphically, a zero is where the graph crosses the x-axis. And in this case, we have two zeros. We have a 0 at -1 and a 0 at 1. So zeros are our x values where the graph, which is right here, this graph crosses the x-axis. We'll see how to do that algebraically a little bit later, but right now just recognize that zeros are where the graph crosses the x-axis.